In this video, I'll walk through two examples of rationalizing denominators when the radical is a root other than a square root. So we have an example of a cube root and an example of a fifth root. Here's the two examples, the fourth root of 16 over 125. Now the first thing I did was I broke the 16 over 125 into two separate fourth roots. Be mindful every time of keeping that index, the 4, in each radical, because that's completely different from this. The square root of 16 is not the same as the fourth root of 16. The next thing I did was I broke the 16 into its product of primes. So I did a factor tree. I don't know if you recall doing that, but it starts by breaking it down into just any number other than 1 that goes into 16. You might have started with a 2 times 8, and then you would have factored that 8 further, 2 times 4, and the 4 is a 2 times 2. Or maybe for the 16 you noticed right off the bat 4 times 4. The quickest route to completing a factor tree is if you get the numbers that are numbers that are closest together. So 4 and 4, you can't get any closer than that. It would be perfectly okay, though, to start with a 2 and an 8. On a calculator, if you're unsure how to do this, you would just take the 16. Notice that it's even, so do 16 divided by 2. That would give you an 8. And then you'd write the 2 and then 8. And then you'd break the 8 further. Because I noticed the 4, I did 16 divided by 4 and got 4. I could then take the 4, and 4 divided by 2 is 2. So we see that the total list of prime factors is 2 times 2 times 2 times 2, or 2 to the 4th. Doing the same thing for 125, I noticed right off the bat, it could be divided by 5 because it ends in a 5. When I do 125 divided by 5, I get 25. And then I see that 25 divides by 5, 25 divided by 5 is 5. So 125 is equivalent to 5 cubed. So now I'm going to rewrite this as the fourth root of 2 to the 4th over the fourth root of 5 cubed. Do you notice that 2 to the 4th can now be removed from the radical? Because there's 4 2's and we have a fourth root, the rule for this fourth root, so this index tells us the rule of that radical. The rule for this radical is a 4, meaning as soon as I have 4 like factors, they can be removed. Here's how it might look. You might see it as a fourth root and something to the 4th undo each other, and we're left with the radicand, the number inside the radical, or 2. In other words, the fourth root of 2, 2, 2, 2, the rule is that you need 4 of a kind. Once I get a group of 4, they can escape the radical. So I have 2 times the fourth root of nothing. There's nothing left in there. So that radical can just go away. We're left with a 2 in the numerator. Now the denominator does not reduce. There's nothing I can simplify in the denominator. But what I'm needing to do when we see rationalize the denominator is I need to eliminate that radical from the denominator. So I need to get rid of this fourth root from the denominator. Now, when I rationalize the denominator, it's okay to have a radical in the numerator. But the first thing I want to do anyhow is I want to simplify any radicals that simplify. So I did that. And then I rewrote this fourth root of 125 as a product of primes. The reason I did that is it allows me to see what is it that I wish I had. What fourth root, because it does have to remain a fourth root. What fourth root do I wish I had so that I had a group of 4 5s? So what I want because the rule is 4. What I want is 1, 2, 3, 4 5s. And you can see I have 3, so what do I need? I need 1 more. If I multiply the 4th root of 5 cubed times the 4th root of 5, I would then have 4 of a kind, and I'd be able to remove that. Oh, sorry. I don't know why I wrote a 4. I could remove that group of 5 as one group of 5. So I write it as 5, not 5 to the 4th, and not a square root or 4th root or any root of 5. It's completely released from that radical once it gets a group of whatever the rule is, and in this case 4. Now, if I'm going to multiply the denominator by the 4th root of 5, I'm going to have to also multiply the numerator times the 4th root of 5. Now here's a trick. If you've struggled with this, here's something I want to encourage you to do. I want to encourage you to use a different color for that part that you're multiplying. You see how this 4th root of 5 over 4th root of 5 is what I've multiplied by? I'd encourage you to do that 4th root of 5 over 4th root of 5 with a different color, as you see I've done here. When I multiply those together, I would simply have 2 times the 4th root of 5 over, now I have the 4th root of 5 times 5 times 5 times 5, so there's 4 of them. When there were 4 5s, it removes from the denominator, and so here we have it. There's the final answer. Let's try one more example. I'm going to rewrite that just below, so in the case you want to look back at it, it was 2 times the 4th root of 5 over 5. 2 times the 4th root of 5 over 5. That was our final answer. Let me erase that so we have a space to do this next example. When I go to this next example, I'm going to see that the 8 needs to be broken down into a product of primes. So 8 is equivalent to 2 cubed. And that's always the first step. Simplify any radical that you can simplify and break any number down into a product of primes. So I have a 7a in the numerator, and in the denominator I have a 5th root of 2 cubed a to the 7th b to the 13th. This one has a rule of 5. If the index is 5, it means we need groups of 5 to be able to remove them. I can already remove some of the pieces, because if I have, let me do this off to the side here. If I have 5th root of a to the 7, that's 3, 4, 5, 6, 7. Then I see that there's a group of 1, 2, 3, 4, 5 that can be removed from the radical. So the 5th root of a to the 7 is equivalent to a times the 5th root of a squared. When there were 7 a's inside the radical, as soon as there's a group of 5, it can be removed. It's not 5 that are removed. When I remove it from that radical, it comes out as one set of 5, so it's just an a. And then there's 2 a's left over. Be mindful of this 5th root, because we've got to keep that index 5 in the radical. So a to the 7th, 5th rooted, is equivalent to a times the 5th root of a squared. Another way you could see that is if I rewrote this with rational exponents, it'd be a to the 7 over 5, and you can see that that reduces to 1 with 2 left over, 1 and 2/7. So that means I could remove an a from the radical. I am so sorry. Let me go back here. I'm not sure why I wrote this. Did you catch that? There's no reason for that to have changed to a 7, right? 7 divided by 5 is 1 with 2 left over, but the denominator stays the same of 5, right? Okay, so we've got this 1 a whole number 1 means we've got one whole a, and then we have a fifth root of, so this 5 in the denominator always defines the index, and then this 2 is our exponent, so a squared. I'm not sure which of these two methods of simplifying the radical makes the most sense to you, but when it comes to simplifying the fifth root of a to the 7, you want to use one of those two methods. All right, so let's write out what we have so far. When we simplify this, we have that this is 7a over, and then we've got an a on the outside, and fifth root of 2 cubed a squared, and now we'll need to simplify that b to the 13. So when I simplify b to the 13th, fifth rooted, do you need to write 13 of them to see how many groups there are? Because 13 divided by 5 tells me there's 2 groups of 5s, right? 5 and 5 more, that would add up to 10. So I can remove 2 groups of 5, so I have a b squared. And then what is the remainder when I divide this? I get a remainder of 3, so there would be 3 b's left over. Let's add them up. This represents 5 plus 5, that's 10, plus 3 more, there's all 13. Now, if you need to, you could write this 13 times 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 to see, okay, there's 2 groups of 5, so that's b squared because there were 2 groups, and then 3 that remain in the radical. So we have b squared and then 3 left over. All right, I'm going to erase this piece. Now we have everything simplified, and we're ready to rationalize the denominator. When we look at this radical, rationalizing the denominator means that I've got to get rid of this radical in the denominator. I can have a radical in the numerator, I just can't have one in the denominator. So I've got a 7a and then ab squared with the root of 2 cubed a squared b cubed. When you look at that, do you see, by the way, that that a over a will reduce? So I could divide that out because a over a is going to be 1. And now to rationalize the denominator, what I'm looking for is what fifth root would I need to multiply to clear out this denominator? Now we've got 2 cubed with a rule of 5 and an index of 5, it's a fifth root. I need 5 2's. I only have 3, so what I'm going to insert in is 2 more 2's. Why am I inserting in 2 more? Because what I want is a group of 5, and a cubed time, or 2 cubed times 2 squared gives us a total of 2 to the 5th power. For the a2, can you see it already? I'm going to give you a minute to try and write that in yourself. How many a's would I need to insert in order to get a group of 5? If you said 3, then you are on the right track, and I think you're getting the hang of this. So to pair up with this a squared, because the index is 5, and I needed a total of 5, I'm going to insert in a cubed. For b cubed, we have 3. So how many more do we need to make it to 5? You guessed it, we need 2 more. Does that look good so far to you? So what would we need to do to counter that? If we're multiplying the denominator, times the fifth root of 2 squared a cubed b squared. We better do the same thing to the numerator so we don't change the value. Why did I just write this fifth root of 2 squared a cubed b squared in the numerator? Because we want a 1. You see that this would just be multiplying by 1. Multiplicative identity is 1, meaning I can multiply anything by 1 without changing its value. So by by multiplying this expression by 1, I don't change its value. I just change its appearance. Let's see what happens here. Now we have a 7 in the numerator. We now have a 7 times the fifth root of 2 squared is 4, a cubed b squared, and in the denominator I have a b squared, and then this 2 cubed times 2 squared comes out as one group of 5, a squared times a cubed. Let me write this off to the side just to make sure everyone sees this. We have 2 cubed times 2 squared, so all together that's a group of 5, so that's why we can remove a group of 2. And then we have a squared, a cubed, all together that adds up to 5, so we can remove one group of a's. And then b, so the third, b squared, all together that's 5, so we can remove a group of b's. And let's see what we would do from there. From here, we would multiply those together, make them look a little bit better, make them look a little nicer. So 7, the final answer could be 7 times the fifth root of 4, a cubed b squared, and in the denominator I'm going to put the number first, the 2, and then I'll put the variables in alphabetical order, a, b, and we've got b squared times b, so 2 plus 1 gives us b to the third. And that's it. That's our final answer. I hope that this video has helped you better understand rationalizing denominators with a radical other than a square radical. But if you do need further help or have a question about this video, please don't hesitate to contact me. Let me know if you need a further explanation.